Welcome to the video for Chapter 4, Part 2, where I discuss process operations and states. My name is John Jolly. Let's continue. So, in this particular video, we talk about process operations, or the application programmer interface that is used to control processes. There are three main APIs that we will use and several other supporting APIs. The first one is the create a new process. Creating a new process involves getting that process ready to actually perform some operation and can contain several different pieces to it. When you create a new process, it gets all the structures in the kernel ready to run. This is what one program does to start another program, or start another process. One process to start another process. Now, the second API is the destroy a process API. There are two ways to do this. You can have a process wish to terminate. When a process has come to the end of its operations, it will call an API that will basically say, I'm done, you can clean up the memory, I don't need it anymore. So that is a way to destroy a process. A second way to destroy a process is for an external process to stop another process, and there's an API for that as well. The third API that we will discuss is waiting for a process to complete. Every process running in a system has a parent, except for one. In fact, that is process number one. All the processes in a system have to be cleaned up finally by another process. That's because every process, when it terminates, has some sort of status. That status is stored in kernel memory until another process cleans up after it. There's an API that is used to wait for a process to terminate or wait for a process to complete so that the state information of that process may be gathered and the kernel structures may be cleaned up. We will show all three of these APIs. There are other APIs that are used for sleep and wake. You can have a process go to sleep and wait for other processes to complete. There's also ways to wake a process that may be in a sleeping state or may be waiting for a resource. There are other APIs that get process state, such as list the running process or show process and I/O usage or memory and I/O usage, and also get some process statistics. There are special programs that we can run, and those will be demonstrated later. So how is a process created? Well, a process is first created whenever another process creates the structures in kernel memory by calling one of the APIs to create a process. These structures are used for remembering the machine state during context switching, as discussed before. Once the process structures have been created, it is then possible to load the program from storage into memory. So this includes the machine instructions and the initialized data. There are two ways a program can be loaded. One, the operating system can load the entire program into memory at once. This is called eager loading and is not necessarily the best option these days, especially with very large program sizes. So you don't see operating systems do eager loading very often. Lazy loading, on the other hand, only loads the parts of the program that are needed immediately by the process. When a process needs a particular part of the program, that program is loaded using paging. And part of the program is put into memory and is allowed to run. Lazy loading is pretty much the state of the art for running processes these days. So this is what we will experience the most. Another thing that happens when you load a program is stack. The stack for local variables is created. This stack is used to keep track of local variables as well as what is called the call stack. Initially, when the stack is created, there are two variables, an argc and an argv, that are put into the stack to be accessed by the main method. Also, when a program is loaded, there is memory allocated called the heap. It initially starts out very small, doesn't have much in it, but it will grow as needed by the program. As the program allocates more memory, for example, using the malloc API, then more heap will be created. This heap will only be let go when the process is destroyed. Finally, the process has the I/O initialized. There is a list of files that are opened by the process. Now, initially, there aren't any files on storage open, but there are 3 files that are opened that are used not for storing files, but for communicating with the console. The first one I'm going to discuss is standard in, stdin. This is where input comes into the program. This is frequently your keyboard. When you're typing on the keyboard, that data comes in through standard in. And programs like, or APIs like scanf or read actually read from standard in those characters. The second file is called console output or standard out. This is generally the console screen. When you perform a printf, that goes through standard out and is displayed on the console. Finally, there is a third file handle called the error output or standard error. This is very similar to standard out, except for it is used to print out error messages when something goes wrong. Usually, to use error output, you have to very explicitly write to standard error. We're not going to do much with this, but I show it here because these are the 3 files that are first created when a process is created. Now, every process, when it is actually in memory, has 3 states. These states are running when it's actually on the CPU, ready when it's waiting for the CPU, and blocked when it's waiting for something other than the CPU. This is a diagram of how a process will transition from one state to another. If a process is in the running state, that means that instructions are currently being executed for that process. The running state is where we want the process to be. That's when actual work gets done. Now, there are 2 things that can happen to a running process. A running process can actually be interrupted and descheduled by the operating system. When that happens, the running process moves to the ready state. And the ready state is actually a list of processes that eventually need to be run. The second way a running process can stop running is if it initiates input or output, such as reading from the keyboard or writing to the console. When a process performs I/O, it moves to a state where it stops or is blocked until that I/O is complete. So the 2 states to exit for a running state is either through being interrupted and descheduled, or when it itself initiates I/O. One is controlled by the process. The process will initiate I/O. One is controlled by the operating system. The operating system will interrupt the process. The ready state can contain 0 or more processes waiting to be executed. This means that the processes aren't actually running their instructions. They have been swapped out. Their context has been switched out and is waiting to be switched back into a CPU. The scheduler will pick processes from this ready list so that those processes can be scheduled to be running on a CPU. This scheduling decision usually involves things like the process priority or how long the process has waited to actually be running. Their only transition from the ready state is to be scheduled to the running state. The blocked state is where processes end up when they are waiting for some sort of external event to happen. This can include keyboard input. This can include waiting for the console to respond. This can be waiting for a hard drive or a network device. All I/O ends up blocked, but other things end up blocked as well, such as waiting for a resource to be unlocked or waiting for a process sleep timer to expire. In any case, whatever caused the block will eventually resolve itself, and when that happens, the process in the block state will be moved to the ready state so that it may be scheduled. Now, there's lots of different ways a process can be blocked, and usually those are maintained on different lists or queues. So there might be a list of processes that are blocked for a hard drive, and those will be on a queue specifically for that hard drive. And when the hard drive is completed, or completed an operation, it will move processes from blocked to ready. So here's some examples of process states and transitions. Let's go ahead and look at this diagram over here. This diagram shows two processes, process 0 and process 1. Now at the very start, one process is running and the other process is ready and waiting for that particular CPU to be let go. The process 0 will run on the CPU in 4 cycles. And on the 4th cycle here, it's actually going to notify the operating system, I'm done with what I'm doing, please terminate me. And so process 0 will actually end its running by being terminated. And so it no longer has a state once it's terminated. The operating system recognizes that the CPU is free and moves process 1 from the ready state to the running state in time step 5. And then process 1 is able to run its instructions until it terminates at time step 8. Over here in this other diagram, we have two processes again, process 0 and process 1. Process 0 starts out running, and process 1 has to wait for the CPU in a ready state. At time step 3, process 0 notifies the operating system that it needs some sort of input or output. So that causes a context switch for process 0 from the running state to a blocked state as it's waiting for the I/O. Because process 0 is now blocked, process 1 is allowed to transition from the ready state to the running state. So process 1 is able to run in the running state for quite a while until it completes. But while it's running, things are happening in the background. Process 0 is blocked until time step 6. At time step 7, something new happens. Process 0's I/O is complete, which moves process 0 from the blocked state to the ready state, meaning that process 0 has to wait its turn for the CPU. When process 1 completes and terminates, that allows the operating system to schedule process 0 from the ready state to the running state and allows the process 0 to complete its operation. This is a good example of what happens whenever a process performs I/O and other processes get scheduled while we're waiting for that I/O to complete. Now, when a process is created, there are internal kernel data structures that are created that represent that process in memory. These are some of the structures. The process structure is probably one of the most important structures that you will use in this class. So understand this structure very well. If you look at this and don't understand what a structure is, then you probably want to review C programming and structures, because this is a fairly fundamental part of C programming. One of the things that the process structure keeps track of is the process memory. This is the address space that we talked about in a previous video. This address space is kept track of within the process structure, as well as the size of the process memory. There's also the kernel stack, and this is just simply a pointer to where that stack is located. This variable here, this process state, the state variable is actually keeping track of what the process state. And this is actually an enum that is defined in another part of the file. Here is the process state enum. And you can see there are several process states that we recognize, such as running. The ready state is represented as runnable within XV6. So runnable is the same thing as the ready state. The sleeping state is the state that we move a running process to when it performs I/O, when it initiates some sort of I/O. So sleeping is the blocked state that we've discussed. These other three states are for internal bookkeeping of the processes. Unused basically means this is a structure that is not used and can be used by a new process. Embryo means that the process is in the process of starting up. It hasn't moved to a runnable state. And zombie is a process that has terminated but hasn't been cleaned up yet. You move to these states, so you move from unused to embryo when a process is very first created. You move from embryo to the runnable state when the process has had everything allocated, and you move from the running to the zombie state when a process terminates. Some of these other variables, every process has a unique process ID, and this is where it is stored within the process structure in the PID variable. As was stated earlier, every process has a parent. And this variable here is a pointer to the parent process's structure. If I want to look at the parent process, all I have to do is reference the parent variable and then the data member within that parent structure. These two variables here, the void chan and int killed, are used for identifying various aspects of the process. Here are the open files for the process, as well as a pointer to what the current working directory for a process is. This variable here, named context, is based off of a structure called context, which is shown over here. Notice that the context is named after various registers, such as the instruction pointer, the stack pointer, and other variables. Now this is for Intel stack switching. This is not for RISC-V. Ours looks quite a bit different in the current XV6. Finally, there is a trap frame. We'll talk more about what this trap frame is used for when we get into scheduling. This process structure represents one process in the system. And all these variables help with context switching when a process needs to move from the various states that it is in. This brings us to the end of the Chapter 4 Part 2 video, where we discuss process operations and state.